hypothesis tests are frequently used in clinical trial in the field of medicine, of human, plant biology, etc. to find out if new treatments, drugs and procedure cause any improved outcomes in patient or plant under treatment. There is also a huge application of hypothesis testing in the business field for market research to determine whether or not some new marketing technique, advertising campaign, or attitude towards a particular cosmetic or car launch in a market cause an increase in the sale. Hence, it is the need of the hour to know how to design hypotheses and what tests to conduct and validate them. There is a connection between hypothesis testing and probability, which is important to understand. This has also been covered in this video. This video also covers type 1 error and type 2 error in decision making and balance them depending upon our problem at hand. So if you feel the need to dig deeper and know more about it, stay right where you are as we are going to bring you all the information that you need right on your screens.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions and I will respond to your comments.
So very quickly, let me walk you through the agenda for today's course. In today's course, we are going to define hypothesis and types of hypothesis. Then we will discuss type 1 error and type 2 error. Then we will discuss the basic concept of 6 sigmas, types of hypothesis test, confidence level and confidence interval level of significance. One-tailed test and two-tailed test will also be discussed, and we will also solve real example of hypothesis testing including t-test, z-test, chi-square test and ANOVA.
Okay. Before actually doing a hypothesis test, first let's understand what hypothesis is all about. So what does hypothesis means? Hypothesis is an intuition that is there, which is not proven. The moment it is proven, it is no more hypothesis. The underlying key point for a hypothesis is which is not yet proven. Yeah. So that's what hypothesis, which is not yet proven. An intuition, observation based on data, may not be based on data. That is something. So that needs to be either proved or rejected. There are only two possibilities to that particular one. Either you reject it or you do not reject it. There is no question of approving it, accepting it. In hypothesis, the important point of hypothesis tests or whatever it is there is no way you can say it is accepted. You can reject it with conclusive evidence or you cannot reject it. But there is no way that I can prove that one. There's no conclusive way to approve that particular one. That's the important element of hypothesis. So what is null hypothesis? Then we have two types of hypothesis. One is, well, we'll talk with examples, then we'll understand. So what is null hypothesis? Hypothesis that does not challenge the status quo. Alternative hypothesis that challenge the status quo. So before we go on to what all different scenarios that are possible, let's take from real life examples. What is all possible? The hypothesis. I think in the very first session, we talked about somebody getting temperature. You go to the doctor. You are getting temperature for the last 7 days continuously in the range of 100, 102, 100, 102. You are using medicines and everything. It is not coming down. Then you go to the doctor. Doctor has what will doctor have? Hypothesis that it could be a malaria. So now he asked you to conduct a blood test. You go for the blood test. Now blood test results come. Based on the blood test results, what can doctor do? He can reject the hypothesis that it is not malaria. But can he accept that it is malaria by that one? Maybe yes, maybe not. Because there are other scenarios also possible which could be leading to that particular one. But there could be certain conditions which categorically tell you that this is not malaria. You say that it is just viral. But some other infection is there. It's not malaria. So that's what the hypothesis. Then you do exercise, then you validate it through certain things. So in a simple scenario, we generally tend to conform with what is normally observed, which is not deviant from the regular observable phenomena. That's what we call as a null hypothesis. The other example the class talked about in the videos essentially is the Coca-Cola bottle. In a Coca-Cola bottle, you have 500 ml, 600 ml. The hypothesis is that by default, you always have 600 ml. Otherwise, in reality, if that is not the scenario, we don't trust what is mentioned there. Every day we'll be doing a testing exercise. So we trust that particular one. So what is the reason or belief behind that trusting? Now I'm getting to a little generic discussion into this. Why do we trust that if the bottle on the Coca-Cola mentions as it's 500 ml and we go with 500 ml as an accepted state, we never go and measure whether it is actually 500 ml or not. There is the thing called as ISI, Indian Statistical Institute, which actually gives the measurement approval. There is all those things that are tested by anything that today you produce 1,000 bottles and give it to me. I'll verify all the samples. Give me 10 lots, 100 lots of 1,000 samples each. Then I verify all of them. We measure where the range is coming, whether all the bottles contain an acceptable range of 500 ml or not. 5 ml less, 5 ml more. It is a very hot season. Given that Coca-Cola is nothing but water, there's a possibility that in a heavy summer, the water likely to get a little this thing. So the quantity might get reduced a little bit. So I may not have exactly 500 ml. I can have 495 ml or 490 ml. Is it acceptable? Maybe yes. Owing to those conditions, I am okay giving that consideration to the company. But instead of 500 ml, let's say the bottle has only 425 ml. Should I believe that with the temperature or these things scenarios are causing all this extra heavy, extra heat and everything causing that 75 ml? Unlikely scenario. There is some goof up going. So as a customer, if I start observing that it is not 500 ml, it is less, then I start making a hypothesis. What will be my hypothesis? The bottle does not contain 500 ml as it is mentioned, but it is going against the norm. What is the norm here? Bottle contains 500 ml is the norm. So which is the accepted norm generally is called as your null hypothesis. What is that you are proposing contrary to the accepted norm is your alternative hypothesis. It challenges the status quo. You understand the concepts here, how these two work? This is very important. And the discussion that we had earlier, what is my population, it is ever changing. Like that, there is an element of subjectivity which is pertaining to or which is very much owned by the business person, the person who is in charge of this thing, who is the owner of the question. Here in this scenario, what is null hypothesis? My null hypothesis need not be your null hypothesis. I think the example in the class again talked about, if I frame that question from a customer standpoint, it could be a different question. If I frame that question from a company standpoint, it could be a different hypothesis. You're getting the perspectives? So the perspectives at times, who is the point, who is driving it might also make a difference between what is the accepted norms. In general scenarios, there should be an agreement everywhere. What is the accepted norm? You go with that, but those hypotheses, the way you consider them might be different from business to business. All right. The company claims that most of the times it is either 600 or more, and it should not be less. The customer says that less than 500 ml clearly. Both are talking about being 500 ml is the core point. That's the accepted null hypothesis for both the parties in that scenario. This is the null hypothesis. It should not be rejected. Or null hypothesis is false, so it should be rejected. This is the true scenarios, actual scenarios. So this is your decision, what you are making based on your inferential statistics. You observed something in the samples. Based on that, you take this call. So now the clear scenarios is when null hypothesis should not be rejected and you don't reject it, it's a correct decision. There's no problem at all. This is a good scenario to have. Similarly, when you should reject it and you are rejecting it, this is a good scenario again. So this bucket and this bucket are exactly good scenarios. Now you go back to your scenario, Prasad, that you talked about, people paying all their bills on due date, essentially by due date. 90% of the customers go by due date. And you actually take a sample. Let's say your population is 10 lakh customers. You can't check for all 10 lakhs. So you randomly pick a sample out of your 10 lakhs customers that you have, take a 20,000 sample and you do that. You realize that 88% of the people have paid on time. So is 88% within the acceptable range of the 90% hypothesis that you have, or the 2% is a big variation that you cannot accept? And now your hypothesis is wrong. You should reject it. If you say that even with a minor variation, it is in the acceptable range, but you reject that particular decision that your customers are not paying on time and you make amendments to the acceptable things. Essentially what I'm trying to tell you, Prasad, I'm not sure you heard it clearly, your problem of people paying on time, right? 90% is the acceptable normal range. That's what your average says primarily, but you say that 88 people are 88% or 87% are paying on time. That's what your test says.
Right.
And you say that 87% is not acceptable. You reject, because of which you take a decision that I will reduce the terms and conditions from 20 days of grace period to 10 days of grace period. So now what does that lead to? It creates concerns, unhappiness, disappointment with people, and your customers will migrate to some other provider. So which is a loss for your business. On the other hand, you say that let's say people 84% or 83% of the people are paying on time. But you say that is acceptable range of 90%, which is not in reality. So then you end up getting money much later than what you anticipate, or this thing, which causes concerns for your day-to-day management or your money revenue operation essentially. So you don't want either of the scenarios. You want to give your leeway to the customers, be in the acceptable range. At the same time, you want to get money on time. So this is the balancing act that you do between type 1 error and type 2 error. So there is no scenario where you have type 1 error completely eliminated, type 2 error completely eliminated. The balance between these two is such that you try to reduce type 1 error by increasing your confidence level to an extent. You are creating type 2 error more, or you try and manage type 2 error in one way, type 1 error increases. So it's a balance that you need to strike appropriately. That's where your hypothesis testing would come into play, and business knowledge will come into play. Where should I draw the line? That's why for somebody else, I'm okay with 90% confidence level. Somebody says I'm okay with 95% confidence level. Somebody says 99% confidence level. And if I had to take one step that is nowhere mentioned in the video, but I connect the dots, the very concept of origination of Six Sigma comes from this one. It's a Six Sigma. So you reduce the standard deviation as much as possible, and still you ensure that most of your data points actually lie between 6 standard deviations from your mean. It's not 1, 2, 3 standard deviations, but 6 standard deviations. That's why we strive for Six Sigma. Imagine a simple example where in reality, in a flight, in airlines industry, should they be operating at 6 Sigma, 4 Sigma, 5 Sigma, 2 standard deviations? Where should they operate? Even one flight, in terms of the amount of losses it causes to lives, money, investments, exercises, the subsequent all investigations that go, the amount of challenges it is going to create is phenomenal. So you cannot live with that. So you are okay the flight being delayed than flight ending up with an issue. So this is where a type 1 error, type 2 error is important. Let's say new medicine, new drug is getting created. When they do the medical tests, they need to be absolutely sure that it does not have any unintended side effects. So what is the accuracy level they should look at? 1 Sigma, 2 Sigma, 3 Sigma. One wrong consequence on testing kind of a thing could lead to any undesirable consequences for the company when it goes into production. So if type 2 error goes there, okay, my medicine is good and everything, and once it launched into the market, they will have undesirable consequences like the Merck. Merck has produced, if I remember correctly, long back, some medicine for arthritis. It reduces your knee pain significantly. People are really, really happy with the knee pain. But what they didn't realize is it actually weakening your heart significantly. This is a long back story, very old story. But because of that one, Merck has ended up paying billions and billions as a compensation to its customers. So these scenarios play a significant role in real time. I know you're spending good amount of time here, but you need to understand these pieces. Now let's move on. So now, what types of hypothesis tests that we do? Now there are 3 different parameters that we do. We consider when you're doing a hypothesis test. It could be based on sample, or it could be based on type of the hypothesis that you're making, or it could be based on the type of statistic that you are using for making your hypothesis. If you're talking of one sample, so take the fruit juice. The one rating that I'm going to capture is I like this fruit juice. Simple question on a scale of 1 to 10. 1, I don't like at all. 10, I like it fully. On that scale, you capture the rating, one metric, one sample. So you capture the sample on that one, you get a statistic. That's one sample test. Now you measure that fruit juice rating in two different places, compare one against the other. It's two samples. Is it clear what we are talking about? And then you do the same exercise with 4 cities, it becomes multiple samples. Now there is an interesting dimension that we can get it with the samples itself. Right now, the fruit juice is already there in the market. I get ratings of likability of the fruit juice currently. Then next month, I'll start making tweaks to my fruit juice composition. Then I launch the product back to the same set of people who have rated me earlier. So it's the same population. There is an earlier rating, then there is a later rating. Two ratings coming into play. Then my hypothesis would be more like, is a fruit juice liked more significantly compared to the earlier version, or it is less likely? Which is the hypothesis? That's the other way to look at it. So one is a paid test, one is an independent sample test. So those are all different scenarios possible from a sample perspective. Is clear with the samples? We'll take examples on that one, but is the concept of the sample, how it plays a role in hypothesis test, clear? The next one is one-tailed versus two-tailed. What is this concept of tailed? An easier way to remember this particular one is the sign of equality, where the sign of equality comes in. If your null hypothesis has an equal sign in it, that's two-tailed, because the alternative can go on either direction. The bottle contains exactly 600 ml is my hypothesis. So volume is equal to 600 ml is the hypothesis. Alternative hypothesis could be volume not equal to 600. It can be less, it can be more. So that's two tails. I'm going on either side of my mean, essentially. That's why it's a two-tailed test. And instead of that, if my hypothesis essentially becomes volume, the bottle contains more than 600 ml, it becomes a one-tailed test. So my base itself starts at 600. So there is no way for me to do anything for less than 600. I start at 600 and go above that particular one. That's one tail. The simplest way to remember. So if your null hypothesis has an equality into that particular one baked in, it's a two-tailed test. If it is not there, it's a one-tailed test. That's the second way of hypothesis testing. The third one essentially is test of means. So different statistics. For a given population, you can say, what is my average likability rating? The same fruit juice example. Or I can talk about how many people have rated more than 8, which is 9 and 10. How many people have rated 9 and 10? Top two box, simply called in market research parlance. Or what is the variance? If variance can be looked at primarily when you're looking at multiple samples. What is the variance between the two samples? Is the variance significantly higher, significantly lower? There is not much of a distinction between the two samples that I'm looking at. That's where you depend on the statistics or the metrics that you are using. So based on these three, so there can be done independently, a combination of these things can be done. So there are different types of hypothesis tests possible. One dimension that is not mentioned here, nor in the videos to an extent, I think videos somewhere it is captured, but one thing to keep in mind is depending on the data also what you are doing. So there is a parametric data or the scale data, what we call as. The other one is a categorical data. And nominal data is primarily an identification purpose. And ordinal data is where you have a rank ordering possible, but there is no quantification of the variation between two levels. You say good, bad, ugly. Good is better than bad, but how much better we don't know. Bad is better than ugly, but how much better we don't know. And is the difference between good and bad exactly same as bad and ugly? We don't know. But we definitely know that good is better than bad and bad is better than ugly. That's one kind of a scaling. It's called as an ordinal data, where you know the rank ordering, but you don't know the extent and the quantification of it. The third data is interval data. Class intervals in a way. A better example normally we take in all scenarios essentially possible is temperature. But simple way to remember an interval data is on that data you can perform addition and subtraction, but you cannot do multiplication and division. So if one place is 55 degrees centigrade, other place is 70 degrees centigrade, that you can say that that place is 15 degrees more hotter than this place. But if one place is 35 degrees centigrade, other is 70 degrees centigrade, can you say it is double? No. That's what your interval scale data is. And the example time and again I quoted in this session, a rating of likability for a fruit juice, scale of 1 to 10. What scale it would be? What data it would be? Interval data. Yeah. Because you have 1, 2, 3, 4, 5. You have 1 to 2 an interval, 2 to 3 another interval, 3 to 4 another interval. Those are interval data clearly. But if somebody has rated 8 and somebody has rated 4, can I say that the one who rated 8 is 2 times the one who has rated 4 in his likability towards the product? So you cannot do that. So basically what we do is all these rating scales, this is just a sidebar information for you to keep in mind, because at any point of time in your firms you're working with market research data, you will see these rating questions more often than not. So rating scales are called as AID scales, assumed interval difference scales or equal interval difference scales. So the hypothesis that goes is the difference between 2 and 1 is exactly same as the difference between 3 and 2. And the difference between 4 and 5 is same as difference between 9 and 10. So that's why they're equally spaced scales, the intervals. When that criteria comes into play, the one who rated 8 is definitely 2 times the one who has rated 4 in terms of the likability. That hypothesis helps in calculating converting the interval data into the next top of the data that we are talking, which is the ratio scale. In a ratio level data, you can do all 4 operations: addition, subtraction, multiplication, and division. So there is an absolute zero, height, weight, money. These are all examples of ratio scale data. So 1 rupee is half of 2 rupees. 10 rupees is double of 5 rupees, because there is an absolute zero reference point. In interval data, you don't have an absolute zero, because my zero reference point is not same as yours when I rate on a particular attribute. So those are the types of data. Based on that type of data, if your data is basically ordinal, the type of which essentially means categorical, or to an extent interval, the tests that you do, hypothesis tests that you do, are slightly different. Whereas if your scale data is, if your data is ratio scale data, the type of the test that you do is slightly different. That's where the classification comes as parametric tests and non-parametric tests. Is the concept clear of parametric and non-parametric? Sure. Now we know there are 4 types of data: nominal, ordinal, interval, and ratio. So nominal data, you won't do any operations on that particular one, basically. Then you have ordinal and interval data. To an extent, they are called as a categorical data. So your interval data can be classified sometimes as categorical, sometimes as non-categorical, sometimes as ratio, based on how you make the assumptions. But think the data as 2 types: categorical data, numerical data, quantitative data. Based on these 2 types, the hypothesis tests that you do are different for categorical data and are different for parametric data. There is a chart based on what type of data, what tests you do. There is like Coxon, Man Whitney, then paid samples, normal when the data is normal, when the data is not normal, when the data is parametric, when the data is not parametric, when it is 1 sample, when it is 2 samples. There are different. There is a table that is out there, a visual. So when we come to hypothesis tests and you start making inferences, there are 2 concepts that we need to be clear of. One is confidence level. Second one is confidence interval. Okay. Confidence level is about how certain are you about the assumption that you are making. Let's say, for example, I throw a die. What is the standard assumption that we have? Sorry, let's say take a simple example. Let me throw a coin which has heads and tails. What is the assumption? The probability of heads is equal to probability of tails. That's, and what is the confidence level that I should go with for that one? Confidence level that you will get equal number of head when you toss a coin n number of times. The number of times the head comes is exactly equal to the number of times the tail comes. What is the confidence level I'm asking? Not number of times it will come. You believe that it has to be 100%, right? but you don't expect it to be 50-50 exactly when you throw it 100 times. So where is this whole thing going? So that's where your normal distribution concept essentially comes into play. The number of trials that you are conducting becomes larger and larger. The deviation between number of heads and number of tails that is appearing will become less and less with the number of trials increasing. That's exactly what central limit theorem says. As the sample approaches the population, the mean of the sample is representative of the population. In reality, it has to be exactly equal. There is no denial about it. But when you do it, where are you drawing the line? If I throw only 5 times, it could be 3-2. There is no way I get 2.5. If I throw it 10 times, it can be 6-4, or it can be 5-5, or it can be sometimes 7-3. But if I throw 100 times, the proportion of variation between the two results becomes smaller and smaller. And if it goes 1,000 times, 10,000 times, it becomes even lesser. And that increases your confidence level. So your confidence level primarily talks about, if I conduct an experiment n number of times, at least 95% of the times, or at least this confidence level, whatever I decide, that percentage of the times, my result will be in the expected range. That's the confidence I take. If you go to the doctor prescribes you a paracetamol for temperature, basic temperature that he sees, the confidence level he has is 95% of the times, at least the temperature should go down when I give a Calpol or a paracetamol. Essentially, that's why he gives it. If he has only 50% confidence, can he prescribe paracetamol to you? So that's the confidence level essentially means. So if I give to 100 people, 100 patients paracetamol, at least in 90% of the cases, 95% of the cases, the temperature should go down. That's my primary hypothesis. The confidence with which you can say that is called as a confidence level. And interestingly, this confidence level is determined by something called as a level of significance. So, what is the acceptable range that you are fine with your experiment failing or not falling in the accepted norms? So, if you go back to your type 1, type 2 that we talked about, type 1 error is what we call as alpha. So your null hypothesis should not be rejected, but you reject it. What is the likelihood that you are making a mistake by rejecting it when you should not be? That's what it is. So getting to the doctor example, what is the likelihood that temperature will not go down when a paracetamol is prescribed, while it is a norm accepted hypothesis that a paracetamol should reduce your temperature? That's what the level of significance. So 1 minus level of significance tells you your confidence level. So level of significance and confidence level are mutually exclusive. It's 1 minus essentially. The total should be equal to 1 or 100%. Is that concept clear? Good. Now when you see your confidence level is 5%, that leads to what are we talking of? Acceptable range. Now go back to the coin toss example. When I toss a coin 1,000 times, what is number of times I get a head and number of times I should get a tail? The ideal scenario is 500 and 500. Let's take only one result. Both results lead to a little confusing and it's mutually exclusive. So it doesn't make sense. One is converse of the other. So let's take the number of times you get a heads. Your hypothesis says that I should get n equal to 500. If my this thing is n is equal to number of trials is equal to 1,000, number of hits is equal to 500. That's my hypothesis. If I get 470 or 530, I'm taking 30 this side or that side. So the 30 variation from 500 is acceptable or not acceptable. How do I draw the line? That is the confidence level. Now you're understanding where confidence level come into play. Why? So you define boundaries. This is the acceptable range of error that I can live with in this scenario. So if let's say I define 10% of the confidence interval. So on 500 heads should come, what is the 10% that I can live with? Variations 50. So it can range between 450 to 550. So if it is coming between 450 to 550, I'm good with that experiment. Then when I do this experiment again, throw the coin 1,000 times, I get 425. then is it acceptable or not? Should I accept my null hypothesis that it is within the range of 500 or not now? Essentially, because it is falling out of the range. So this, based on your confidence level that you defined, you are defining a lower bound and upper bound. The lower bound is 450, upper bound is 550. This 450 to 550 interval is called as your confidence interval. Are you connecting the dots between confidence level and confidence interval? You define confidence level, which leads to automatic creation of your confidence levels. And what is that confidence level that you can decide? It depends on your business. As I talked about earlier, if it is an airlines industry, if it is a drug pharma industry, what is the acceptable level that you go with? 95%, 90%, and you put people's lives into risk. And let's say, for example, you are launching a fruit juice. If the likability is around, I would say 8 is the mean that I would expect, and it goes at 7, can people live with it? Yes, absolutely. I am fine with it because it is not impacting people's lives or it is not having a grave concerns. So as a business, you need to decide what is the confidence level that you need to trust it with. Your hypothesis testing is sitting on that pillar of confidence level. So now take that confidence interval. As we talk of the example of Coca-Cola, if your mean of 600 ml is standing in this line at the center, and if I define 10% as my interval, where should that be? 10% of 600 ml would be 60 ml. So it should be operating between 540 and 660. So, which is, I define a boundary here as 540 and 660. So any bottle, when I randomly pick a bottle and check how much quantity it has, if it falls in that range of 540 and 650, 660 essentially, so I say that that bottle conforms to the normalcy. Otherwise, I have to reject that this bottle is an exception. So that doesn't conform to what the normalcy should be. And these edges that we're talking about, this other side, when you are doing a one-tail test versus when you are doing a two-tail test, operate differently. Because you are taking only one end, and in your confidence interval, you are taking on both sides, your confidence level that you are defining will be split into two exact halves. One half is on this side you reject, and the other half on this side you reject. Why we define this exactly as same values? The very simple reason is this is a symmetric distribution. This is the property of the normal distribution. When it is exactly, it's a mirror image. If you draw a mean line and you fold it, they should be looking exactly the same. That's what a normal distribution tells you. That's why you divide it into exact halves. Is that clear now? Why the application of why a normal distribution should be a bell-shaped and why it should be symmetric in nature? That is the reason. The moment this is not normal, you cannot define exact intervals on both sides. You can consider for your purposes, but it may not be the case also. Is it making sense, folks? Anything in this white region is rejection. So you're rejecting 2.5% values on this side and 2.5% values on this side. And from a probability standpoint, what is the maximum probability you can get? 1. Minimum probability you'll get is 0. So it is mathematically this whole area under this curve is how much? Area under the curve? 1. This whole area space under this curve, this is called as the area under curve. Is called as your probability region. So the value has to be between this one and this one. So there is a value of acceptance, value of rejection. Your value of acceptance is nothing but your probability. So in this scenario, your probability is 95%, which is your confidence level. So that's how you connect your probability, your stats, hypothesis tests, everything that you do, and mathematics also. And to do this, you can do integrations, you can do differentiations, you do a lot of calculus around this particular one to get the area under the curve and everything. But that's a different topic. I'm just trying to connect the dots for simplicity. But is this part clear? So this is a two-tail test. When you come down, the same example, you see this whole area is covered under this one. So here you're rejecting only one side. The rejection area is only on one side. So here you took 0.025, 0.025. We are taking 0.05 in this scenario. This is where you say that you have a one tail test. The bottle has definitely less than 600. So the company has to prove that the bottle has at least 600 ml. If it is less than 600, you fail it. But what is an acceptable range that you can reject it? So instead of looking at both ends, you take everything at one end primarily. Simple examples that are out there in this one, and then we can jump on to the other topics. See this example for a hypothesis test. A study was done to see the effect of the presence of dogs as pets have on kids, taking the kids in the age group of 10 to 18. So there are two groups of teenagers who have dog. I think they took a sample of how many people, some 10, 15, whatever it is, these people. Then a set of people who do not have a dog. These are the samples that they have taken. Now, what is the question to have? Do dogs have a significant effect, either positive or negative, on the cheerfulness of kids? That's the question. So there is a set of people who have a dog as a pet. There is a set of people who do not have dog as a pet. And the presence of a dog as a pet, will it lead to change in cheerfulness or difference in cheerfulness for the kids? It could be positive cheerfulness, it could be negative, whichever it is. So this is the question that we have. We want to answer this question. So let's start answering these questions. So I think you would have seen on the video, this is the standard template that you will use for doing a hypothesis test. First, you define what is your hypothesis. That is a null hypothesis. Then you define your alternative hypothesis. Then that also includes whether you are defining a right tail test or a left tail test. This go hand in hand. Then you have a one sample test or a two sample test. Then is it a test of means or proportions or variance? Which of this particular one are you dealing with? And then which statistical test do you think is appropriate on this one? These are the questions that we have. Now let's start answering. So what type of hypothesis are we going to create in this one? Now you understood the question, right? Having a dog at home may not have a difference is the norm that we go, because we say that there is no difference between two groups whatsoever is our basic hypothesis. Now you're bringing in one variable or one factor in between and want to measure the impact of this factor. So you feel that already there is a difference, you don't measure what's next. So you assume that there is no difference, then you bring in an element that might cause a variation and say that, okay, now there is a difference between these two, so this factor has a bearing on that one. Are we clear how we are formulating the null hypothesis? Yeah. So the null hypothesis we go with is there is no difference in the mean happiness or the cheerfulness that is provided for the two groups. People who have dogs as a pet, people who don't have dog as a pet. There is no difference is our null hypothesis. Then automatically your alternative hypothesis, yes, there is a difference. That's the alternate hypothesis that we go with. Then now you know what is null. You know what is alternative. It should automatically tell you what it's a one tail, right tail, left tail, or one tail, two tail, what we are trying to do. It's a two tail test. So now the question is whether it is a one sample test or two sample test. It's a two different independent samples that we are dealing with. Good. So next question, is it a test of mean, proportion, variance? What type of test we should use? No, it's a numerical data. It's the means you can calculate on this course. So it's a test of means essentially. So you do a test of means of independent samples. That's what the test you essentially do on this one. This is how you go with. So average score of kids, mean 1, standard deviation 1, 7.73, 1.24. But that is with dogs. Without dogs, you calculate again the mean and standard deviation. So the difference between the two means essentially 0.01. Which is the difference between two standard deviations going on. Yeah. So okay. So now null hypothesis essentially pets have no effect. Pets have an effect on this particular one. Alpha we defined as 0.05. Then T critical is a calculation using this formula M1 minus M2 essentially. So then under square root of S1 square. S1 is the standard deviation for the first one. S2 is the standard deviation for the second one. Then N1 is sample size of first one, N2 is standard size of second one. So you get a T statistic value of 0.35. So what is this telling? how do we interpret this t statistic? Table, you will get the t value. Once you calculate it, you do this, or through different means you can get the tables. But what does the table tell me? What are my general levels of different significance levels we are looking at? So which means what is the confidence interval I should have?
95%.
95%. For 95%, what is the value, corresponding value of a t statistic? That's what you should compare against. So for a 90%, you will have 1.645. For a 95%, you will have 1.96. And for 99%, you will have 2.58. Those are three values I think you should have back of your mind always. So if you compare against that particular one, if this value is greater than plus 1.96 or less than minus 1.96, because you're doing a two-tail test. So you're doing plus or minus 1.96 is the range, minus 1.96 to plus 1.96. Is this value lying in that range or outside of this range? Within that range. So you don't reject. If it is falling within the range, you accept it. Isn't it the case? If it falls within this range, accept in the sense we should not say accept technically. We fail to reject the null hypothesis. This is what we should say. There is no acceptance per se. So we don't reject the null hypothesis. So as a result, so what does that mean we fail to reject the null hypothesis? There might be a difference between two groups we don't know. We cannot just prove that. That's all. Benefit of doubt. The values that I was referring to was a Z test, not a T test. Now, so what is the number of samples that we are looking at? What is this one? How many values we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe less than 15, 20, roughly, approximately, for this group and this group. So that's a small group we have. We don't have a huge sample size. You're dealing with a small sample size. So when your small sample size is less, it cannot be normal distribution. Then you can't use a Z statistic. You have to go with a T statistic. As I said, if you remember earlier, with the T statistic, we try to make some assumptions and make the measurement a little stringent, essentially. So for a normal 95%, we should have looked at a confidence value of 1.96. Thanks for bringing it. But for a T test, for a T statistic, its range is around plus 2.11. If it is a Z measurement, when it is a normal distribution completely, Z distribution, you could have lived with 1.96. But for this one, the range has increased from 1.96 to 2.11. So it is actually 0.15 more, the range. So you are making the measurement more stringent to reject anything. Because you have less sample, you cannot conclusively reject. So normally 30 is at least base number that you should look at as a sample size to ensure that you are hitting the normality assumption. But 30 is not exactly that you have a normal distribution. It depends on your population. Let's say, for example, how many customers visit my website, and if I go with 30, do you think that will give you the reasonable estimate?
No.
Million customers might be visiting my website every day, and if I just go and operate on a base of 30, it is not at all representative on this thing related to my population. So I should be really looking at hundreds and thousands so that I can confirm, definitely say that my data would be normal, and I can follow the normal assumptions. But if my population itself is only around 70, 80, 100, 150, 200, maybe 30 could be a reasonable number that I go with. But statistically, following the central limit theorem, all calculations and magic that goes behind it, 30 is that magical number where all people believe that you can start applying a normal distribution on your data. Then this 2.11 will become 1.96. If you had data points of not instead of 16, you had 17 data points should have been there, because degrees of freedom is 16. So you know how to calculate degrees of freedom? It's n minus 1. Simply, if your sample size is n, degrees of freedom is n minus 1. If you go to the T table on the clocks table that is out there, the logarithmic tables and everything, if you look at a T distribution data, you look at 16 as the degrees of freedom, and at 95% confidence interval, you get the T value as 2.11. This is how you go ahead with a T test with two samples, which mostly is the scenario that we apply. So this is explanation of the same thing. The test we just performed is called as a two sample t-test or independent samples t-test or students t-test. These are called students tables, as I was telling about the clocks tables and everything is called as a students tables. So we perform this test to see if there is a statistically significant difference between the means of two groups. The null hypothesis, that is that there is no difference. Alternative hypothesis, that there is a significant difference. To perform this test, we need to apply one independent qualitative variable with two levels and one dependent quantitative variable. That's what we have seen. There is a difference. Cheerfulness is the qualitative variable and quantitative variable is the scores on that particular one. So let's jump on to the next one. So this is another example. So this is an interesting example to look at. The following example is an income data of blue collar workers who are at the same skill level. There are two groups of workers: workers of the textile company Loris and Co. and workers of the general population. We want to check whether the variance in the income of Loris is higher than general population. So now the data that we have is mean and variance of a general population. When we say general population, it is your full population, whole population. The mean is 100 and the variance is 16.11. And Loris population, how many data points you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 data points that we have. So now how do we go about it? What are the questions? The question what we want to answer is there a variance in the income level of Loris group higher than general population? So what is the first thing that we should do? Calculate the mean and variance for Loris group, essentially, right? Once you get those two metrics, the mean and variance, essentially, your step one is done. Now we come to our set of questions that we will answer. Is it a null or an alternative hypothesis? What would be the null and null hypothesis for this? So basically, there is no variance. They are equal. That's what we would look at, right?
Yeah.
What is the alternative hypothesis? So now what type of a test it is? Right tail test. Now, this is the important question. Is it a test of mean or proportion or variance? What we are asking is whether the mean is higher or not. We are asking whether there is a variance in the income levels. Where it's a test of variance. Now you remember the first point that we made when we started off distributions and the central limit theorem basic hypothesis. The sampling distribution of mean of samples in a given population is normal. But if you take variance, so what distribution we should apply? Chi-square distribution is what you should apply, right? We'll come to the solution to this one, but let's understand what chi-square distribution essentially is. Then we go to solving the problem. Okay. So when we take many samples of the same size from the normal population and find the sample means, they follow normal distribution, same point what we have been beaten to death till now. But when we take many samples from the same size of normal population, find sample variances, they do not follow. Instead, they follow something called as a chi-square distribution, which is dependent on degrees of freedom. Degrees of freedom gives you the variation of the distribution. Even now, even here, what you need to remember is higher the degrees of freedom for your data, higher the possibility that it is getting closer and closer to the normal distribution. The same point. It doesn't matter whether it is a normal curve, whether it is a skewed curve, whatever it is, area under curve is always one. So that's a given thing. So let's not bother. The last point, we'll discuss this and then we'll come to this one. So this is how a chi-square distribution looks like. So this is how, if you plot your variance data, if you plot variance in that place, you can take this as an exercise when you get that file and start plotting variance in that data. You plot variance, the variance will come like this. So this is a right tail data essentially. But important point you need to observe is the three different curves they are putting across here. What is the degrees of freedom telling here?
Yeah.
5, 10, 15. Does this tell you something? Does that ring a bell? There's an intuitive understanding to this one. Normal, exactly. So that's the point you need to keep in mind. So when you have very high degrees of freedom, it more or less resembles normal to an extent. But the variance, the amount of variance comes down. to an extent. The variance is also coming down. You see the length of this thing? So when you have small samples, you tend to have a very high variance. Probably you could see that very easily, right? When you have only 10 people who are giving you a rating, calculate the average. For one person, the average keeps changing very highly. But as your sample size goes to 100, 200, 300 and everything, the variation in means moves only at the second decimal, third decimal, that's all. It doesn't make difference in the first decimal at all. So that's where your normal distribution hypothesis comes into play. That applies for your variance also to look at. But still there is an element of skewness, but that will come down. And your variance will also come down as your sample sizes increase and tend to go towards population. That's the second point you need to keep in mind. Now, the important point. The cumulative probability runs from right to left. In all the normal distribution, we always started at this side. And it says 0. It is the negative side of this one. Then 0, which is a mean, 0 mean at the center. Then +1, plus this thing on this side. But if you are doing a one-tail test, you assume 0 on this side and then you go like this. Whereas, so then the area under the curve is at the end of the day is cumulative probability for you always. For a chi-square test, you start measuring from this side. It starts from right and goes towards left. So 0 is on this side and 1 is on this side. Why so? So in which zone you have maximum data points lying? Left side. So that's why it starts on this side. If it has been symmetrical, it doesn't matter which side you start. But in this side, there are fewer data points here and the data points keep on increasing from this side to this side. That's why you go from right to left for the cumulative probability calculation. So given that this is the chi-square test of variance, one other point in a broader context to keep in mind, chi-square test has two types of tests. One is test of independence, two goodness of fit. But predominantly the other area where chi-square test can be used is when your data is categorical. When your data is normal, you predominantly use the t-test and z-test and the other world completely. When you have a categorical data, you tend to come to chi-square test. Okay. So now let's solve the problem. Is this example clear? Is this concept clear? See, the rest of the thing here is exactly the same. That's why I'm not reiterating. As I said, you have your alpha value, alpha by 2 on this side, alpha by 2 on this side. We took exactly the same thing. But the region this alpha by 2 represents is smaller on this side, whereas this region could be much higher on this side. Because there are fewer values, the tail is longer, so you get a broader region on this side, smaller region on this side. So this is the problem. Lori's example. So the total population, mean 1, variance 1 is 116.11, which is already given for us here. And then we calculated the same thing for Lori's group. We got 104 and 40 point. See, the mean is marginally higher, but see the variance that is. Given that this is a broader population, the variance is small actually, because it takes so much of data. Variance can be less. When it is only small set of data, you have a much higher variance. The same point what we are talking about. So now n is only 15. That's why you see a much higher this thing. And degrees of freedom correspondingly becomes 14, n minus 1. So now what is your null hypothesis? There is no difference in variation. Both are the same. Alternative hypothesis, Lori's group has a higher variance compared to the general population. And we are doing the test at 95%. So you calculate the chi-square critical value from the tables. There's a chi-square tables in the students table book that we get. And for this particular one, when you look at the 95% interval or the alpha level of 0.5 and this degrees of freedom, you get 23.68 as your chi-square critical value. Like you got T critical in the previous example, you get chi critical here, just 23.68. So the statistic, the way you calculate essentially is for this data you got, whatever you calculated, chi-square is equal to degrees of freedom of V2 by V1. So this comes to 35.62 essentially. Chi-square. It's not chi-square. Actually, it's a Greek letter, which this line actually goes much longer than this. So they are putting just x square there, essentially this. So the value you get is 35.62. but the chi-square critical value is 23.62. So your chi-square value is much higher than this. So low-risk group has significantly higher population variance on this one. So in with Python and everything, with all these libraries, you don't need to. All these programs throws these at you. Right. So now coming to this one, we did chi-square test of significance, the same formula. Sir, I think I did not go through this one, but I explained the same point. So you draw the lines at the same significance level, you get this longer line and you get a smarter this one, but you get more data points lying in this range. Fewer data points on this one. This is two tail versus this is one tail. Same pieces we touched upon this one, but it's exactly the same thing. Simple concepts. The formula n-1 is your degrees of freedom into variance of your sample by variance of population. So this is a normal x square. This is written, but I think see here you see a different chi-square written as a representation, just for reference. Okay. So now you saw the previous example where we took two samples and tried to do the variance. But here look at this. Three groups of samples of factory emissions of different plants of the same company were collected. The score is computed based on composition of emissions. We want to find out if there is any inconsistency or difference across three groups. Group A, so much data. Group B, Group C, the emission data that is coming for three groups. What are we trying to see? Inconsistency or difference? It's not just the means. Inconsistency or difference between three groups. So far we have been operating with one or two samples essentially. Now you are getting into three samples. So the life is becoming more interesting now, which we are tending towards more real world examples here. So can we do any of the regular t-tests or other tests that we have been talking so far? No, you cannot. So we need to resort to something called as ANOVA. What does ANOVA stand for? Analysis of variance. Good point. So when you did chi-square, that is basically meant for two samples there. You did for the variance differentiation between two samples. But when you have multiple samples, so it's not just three. In the previous example that we saw, three, you can go to n number of samples, k number of samples. So analysis of variance, the fundamental hypothesis you go with is all samples that you have the same mean, same variance. That's what it is exactly. That's what you the means are same, you analyze variance. If the means are not the same, then there is not much of the variance. See, between mean and variance, it's a good idea to draw something here. Let me go to the whiteboard if I can. Three normally distributed curves. Assume so. So can you differentiate between these three curves that are there? What is what? Have any sense?
The mean is
For all the three, the mean is the same. It's the same mean. So all the three normal curves, normal distributions are happening around the same mean, but with varying variance. Understanding this? This is what we do in the analysis of variance. This is sample 1. This is sample 2. This is sample 3. Have the same mean. When you know all your, you can calculate the variations in the variance and how it impacts you only when all means are supposed to be the same. That's what your null hypothesis. So automatically the alternative hypothesis is not all population means are equal. Let's say, for example, instead of this, let's take a broader one. For example, let's say for some reason this curve like this, and I have a mean here. What is this? This is another sample. So let's say this is mu1, mu2, mu3, and this is mu4. What does this prove? Mu1 equal to mu2 equal to mu3, but that is not equal to mu4. In that scenario, my alternative hypothesis comes true because not all population means are equal. Importantly, what you need to keep in mind is it does not differentiate or tell you which is different. It tests whether all are in the same acceptable range or not. If it is not, it will tell you very differently. So for at least one pair, if you are using three samples, it could be A equal to B, A equal to C, B equal to C. It doesn't tell you which is different, but at least one pair has a different means compared to the other one. That's what ANOVA tells you. This is one. So the same problem will come to the solution again, this particular one. So one way ANOVA, what exactly it is? So the one way ANOVA is used to, so the ANOVA has two types. It is one way or two way. Actually, there is something called as MANOVA also, multi-way ANOVA. But for the sake of simplicity, keeping things into the simple under the carpet for now, you don't use MANOVA in majority of the scenarios, so don't bother about MANOVA. Only you need to ANOVA. And ANOVA is also, know it theoretically. What you are important to know is the F test that comes into play, the F value. This primarily you use when you are doing a regression. Linear regression, when you do, this F value comes into play. And when we talk of linear regression, then we'll get a little deeper with ANOVA on understanding how the ANOVA value makes sense. But the fundamental concept is you have a higher F value which is significant. That is important for you to go ahead with regression. If you don't have a significant F value, you don't do regression. That's the base amount of information you need to remember. Okay. But in real life scenarios, majority of the times you don't end up using much of ANOVA essentially, other than that. So the one-way analysis of variance is used to determine whether there is any statistical significant differences between the means of two or more independent groups. That's what we discussed. And for this way, this ANOVA, the ratio between the group variability to within the group variability follows an F distribution. So let's say how many groups we are taking here. Let's take this example for how many groups we are looking at. 3 groups. So the variability within these groups versus variability across the groups. Within A, within B, within C, how is the variability? Versus between A and B, A and C, B and C, how is the variability? That's the point that we are talking about here. Just to quickly. Based on that, you try and plot those variances into a graph format. That distribution is called as the F distribution. When you use a when you use two samples and drawn a distribution, what distribution you ended up with? Variance of just two samples, you ended up with chi-square distribution. When you use multiple groups like that, you end up with a F distribution. And your null hypothesis is same as there is no variance between the thing. Alternative hypothesis, there is a difference between that particular one, at least one pair. Okay, so that's the thing. So then each of these things calculates by the formulas. So let's start with this example. Are you clear with the concept? It is as simple as that. You calculate the variation within the group and across the groups, and then you divide one by the other. Then you get the F score. If that F score is, again, there is an F table kind of a thing. That F table with the given degrees of freedom will tell you a F statistic. And if that F statistic is, your calculated value is higher than the F statistic that you're getting from the table, it is significant. Otherwise, it is not significant. The logic and process is exactly the same. We'll do that here. So degrees of freedom between k minus 1 is equal to 3 minus 1 is equal to 2. So how many? K is nothing but the number of samples, right? You have A, B, C, 3 groups.
Right.
So 3 minus 1 is 2. That is degrees of freedom between. Degrees of freedom within. So what is N? In total, how many values you have? All 3 groups together, how many values you have? 59. And minus K, number of groups that you have. 59 minus 3 is equal to 56. So the total degrees of freedom is nothing but degrees of freedom between plus degrees of freedom within, which leads to 58. For the above degrees of freedom, F critical is equal to 3.161. As I said, you get the F table. From the table for this degrees of freedom, for the given confidence level that you are looking at, you get a F critical value of 3.161. Now the rest of the process begins. So mean value of A group, this much, B is this much, C is this much. So on the visual observation, do you think is the means the same? Misleading, right? This is completely off the place. Other two are certainly somewhat closer. So now overall mean is take all the values, total sum divided by this is 48.54. Even the overall mean is going on this side, but B is way off essentially. Now you called sum of squares of total this thing is equal to the same way you calculate the means, xi minus overall mean. Xi is you take each of the 59 values that are there minus the overall mean, which is your 48.54, square and add up all of those sum of squares comes to this particular one. This is the total. Then you calculate within for group A, group B, group C, you calculate the mean differences and square and add up them, the sum of squares. This is what you get. and sum of squares within, between the groups. So you calculate the total within and between. Between is nothing but total minus within is equal to this much. You just substitute that into the formula. So the mean squares between is equal to SS between by degrees of freedom, this much. So the same for between, within, you calculate this, and F statistic is nothing but MS between by MS within. Your 5.73 versus what is the value that we got here? Critical value? 3.6161. So 5.73 is higher than 3.161. So it is significant. So we reject the null hypothesis. And even by visual observation, we saw that this is very different from this particular one. Just if you want to do an exercise, when this file is shared with you, change this one from 41 to some 53 or 49 or something, and then do the exercise. Then it would be interesting how close this 3.161 versus these values would come to. It's an exercise you can try. Okay, so this has another example exactly on the same lines. So a study found that as of 2015, the world population of 7.7 billion, so many billions are diagnosed with HIV positive. Of 1.3 billion Indians, 2.1 millions are diagnosed positive. So this is a population mean and population, this particular one, this is with respect to India. So how do we do this analysis on this one? Null hypothesis is the population of AIDS significantly different in India to that of the world. So if you look at 1.3 over 2.1 versus 7.7 over 36.7, you can get roughly what is the proportion that you are getting it. But are they significantly different, or more or less they are in the same range? That's the hypothesis. So again, you go with proportion of AIDS in this particular one. So 0.0047 in the world, you calculated the difference. This thing is 47%. Proportion of AIDS in India is 16%. So you calculate the Z statistic. P sample 0 minus P sample. Oh, okay, this is not the. Sorry, I think the ordering of these slides were different, I suppose. This is basically test of proportions. We covered test of means, test of variance, but test of proportions we did not cover. So this is test of proportions. So basically calculate proportions. So this is the Z statistic. P sample minus P population that is out there. So 16 minus 47 by 16 minus 47 divided by the total population out there, that is N essentially, which comes to your minus 65.68. So that is, if this value you calculate the Z statistic, this is significantly higher, significantly different. I won't call higher, significantly different from the world population. I mean, just looking at the proportions, you can see that 0.16% is significantly different from 0.47%. But just this higher statistic. So even if you take 3 standard deviations also, the value is somewhere around, but 3 standard deviations, 2.58. But here you are getting minus 65.68. So take that as plus or minus 2.58. It is way beyond that particular value. So it is significantly different. That's what it means. So that's an example for test of proportions. The only piece is, let's say they are comparing between world, which has the population parameters, and India. And let's say, for example, tomorrow you compare India against China and you got China numbers. How do you do that? So there is a slightly different formula for that. Basically, what you do is proportion of India minus proportion of China divided by proportion of India minus into 1 minus proportion of India multiplied by proportion of China into 1 minus proportion of China divided by 1 by n square plus India sample size square plus China sample size square. So that's the formula essentially comes. So don't bother. There is a formula available everywhere. You do a Z statistic using Python file, you will easily get that. But that's how you calculate. Instead of comparing against the population, you compare against another sample. The formula slightly changes of calculation for proportion on that.
So very quickly, let us summarize today's video. In today's video, we understood hypothesis null and alternative hypothesis. We also understood good scenarios of rejecting and not rejecting null or alternative hypothesis and type 1 and type 2 error and the cause of these errors. We understood that based upon our problem under study, we increase type 1 or type 2 error. We try to create a balance between the two and validate the hypothesis. We consider 4 parameters while doing any hypothesis testing. First, based on sample. Second, type of hypothesis we create. Third, type of statistic for creating hypothesis. And fourth, depending on data. nominal, ordinal, interval, and ratio. We understood that confidence level is about how certain we are about the assumption we are making. We also understood the connection between probability and hypothesis testing, one-tailed test and two-tailed test, and when to use which test. We understood that higher the degree of freedom of the data, there is a higher possibility of getting normal distribution. Degrees of freedom gives the variations of the distribution. We understood and solved examples of the test of mean, test of variance, test of proportion.
If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new update or video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on the video for any query or suggestions, and I will respond to your comments.